In this video, I'm going to talk about the Fourier analysis. So this is the first part of the Fourier analysis. So I'm going to focus on some basic introduction. Okay, before talking about Fourier analysis, let's talk about integration. So in the previous lectures, I talked about the integrations, including the standard single variable integration, the double integration, and triple integration. They all involved sort of, here I use a simple example, which integration just very standard integration from f of t from 0 to t and over t. So that's a standard integration. You can also consider double integration or triple integration. So those one involve the integration of functions. So typically this can be complex, especially when ft, this function can be really complex. So one idea that people have thought about is, hey, can we write a function in a form? The idea is I want to write a ft in another form. Let's say something that I know. This one typically called base functions. I can write this as summation of k from 1 to infinity. Could be infinity or could be finite. This one has ai typically times g's of let's say use ak and gkt. So the gkt should be fairly simple, and you know how to compute that. And ak just the coefficients. If we can write this one in this way, now the integration of ft, whatever dt, just same as the integration infinity or any positive number, integration of ak gkt dt from 0 to t, for example. The goal here is to figure out this one also called the gk from k to 1 to infinity or from k to any positive number n. They call it basis function. The goal is we want to find a basis function such that integration of this guy is very easy to figure out. The only difference for different function will be just the parameters or coefficients of ak. So the first problem is, can we write this ft in a way which can help us compute the integrations or other computations? Okay, so that's the main idea. People try to look at how to write the function ft in this form, which means it's a summation of the basic function with different coefficients or different weights. Okay, as a matter of fact, people have thought about how to do this. So one typical approach that people have thought about is to use a tail expansion. So tail expansion is one way we can write this ft in a different approach, in a different way. So if you recall the tail expansion, if you don't know this one, you can check the Wikipedia or any online resources to find out what is the tail expansion. So by using tail expansion, you can rewrite ft as, this is any fa plus the derivative of a of ft, then evaluate a divided by 1 factorial times t minus a plus the second order derivative of ft over t evaluated a divided by 2 factorial times t minus a squared. You keep on doing this. So this one will be the triple derivative of ft at t with respect to t at a divided by 3 factorial times t minus a to the cube. Okay, you do this one, so on and so forth. So the Taylor expansion says you can write this ft as sort of summation from n of this whole bunch, this piece, for n from 0 to n to infinity. Okay, this is what a Taylor expansion says. You sort of can consider this one as we have basis function as, here I have time 1, the base function is 1, the base function then is t plus a, t minus a squared, t minus a to the cube until t minus a to infinity, basically. So you have base function like that. So you can write any function ft by using Taylor expansion in this way. Here's a fn of a. This notation means the nth derivative of ft with respect to t, and then evaluate at t equals a. So you might want to say, what is the issue with this one? Because one of the issues we can find out is we have to compute the derivatives until the infinity. You have the f, let's say f100 a. You have to compute the derivatives 100 times. Basically, you do like f first order derivative, then you take a derivative again, whatever, right? You take a derivative again, so on and so forth, which make it really complex in order to figure out the exact form. Okay, so that's the issue with the tail expansion. Okay. Now, what do we have any other options? Can we find a better one? Okay, so this is what a Fourier analysis is about. Fourier analysis talks about how we can write a function ft into what do we call a Fourier series. Okay, in other words, we want to write this ft function as a number of sums in terms of the sines and cosines. Okay, so this is also, so next question is, what is the Fourier series? So typically the goal is we want to write this ft sort of into the summation of a number of sine function and cosine function with parameters. Okay, so you sort of can see this is sine kt and cosine kt. They are for different k as a base functions. So the nice thing for this one compared to the previous one, so as I show you later on, you don't have to do a derivative in order to figure out the ak. You have to find some sort of integration to figure out ak. And also the sine kt and the cosine kt, they have very nice properties that people can use. For example, the sine derivative will be just k times cosine kt. So sine is cosine, cosine is sine. Cosine kt, take the derivative with negative k sine t. So it's a very nice property. And also there's some other properties that called orthogonality properties, and which means integration from negative pi to pi, you sine kt, for example, times cosine kt, and you over dt. This will always give you 0. The orthogonality property will help us a lot when we compute all the stuff. Okay, that's why there's a lot of benefits by using the Fourier series. Okay, the other one, the Fourier series is useful because Fourier series also talks about the frequency response. This represents the frequency domain, which means you can write the signal ft. This is in the time domain. This is in frequency domain. We can just convert to a frequency domain. So there are a lot of applications when we convert data from the time domain to the frequency domain, such as voice recognition, voice processing problems. Okay, so that's why there are a lot of important applications by writing a function ft into its Fourier series. Okay. So I talk a little bit. I just talk briefly a little bit about why we do the Fourier series, because first of all, sine and cosine, they have very nice properties we can use. The integration of derivative of sine will just become cosine, and integral derivative of cosine will become sine. Of course, you could have a negative sine or positive sine. And also, like I mentioned before, sine and cosine represent different frequencies in the frequency domain. Also, sine and cosine has property of even and odd functions. I'll talk about it later on. What is the even and odd function? Then there's very important properties for the even and odd functions that we can use to simplify a lot of computations. So the next question is, how do I write a function into the Fourier series? Since this is very important, right? I want to figure out how do I write a function ft into a Fourier series, right? How can I do that? Okay. So there are basically two steps we write a function into Fourier series, depending on the type of function we're talking about. The first one is called a periodic functions, which is the main part I'll talk about in the next several lectures. There's also a non-periodic function, which will be part 2, because non-periodic can be a little bit complex, but actually it's based on the result from the periodic function. Okay. The reason we talk about periodic function because the sine wt and cosine kt, they are periodic functions. That's why we talk about periodic function. So now it becomes a problem. What is the periodic function? Because we haven't talked about it very formally. So let's talk about what is the periodic function and some of the properties of periodic function. Okay. So this picture shows, so this is a given function of ft at different time, assuming this pattern will continue, which means I'm going to continue the same pattern keep on going, and also keep on going on both sides, negative and positive sides. So a periodic function typically has this property, which is given by ft will be equal to ft plus this big T. Okay, this is big T here. This big T is also called the period. Well, this means your ft at a certain time, and if you shift the t by some t, positive t, ft is the same. It remains the same. It will be the same. This has to be true for all. This means for all t, there exists a positive t such that this is true. Okay, then ft is called a periodic function. For example, here this is a function I give you ft. So assuming that this pattern will keep doing the same pattern. So if you do here, this is -1, this is +1. So this sort of see if I'm staying right over here. Let's say this is f -1, for example. Of course, here it stands to 0, right? This one is the same as you shifted to 2, okay, which is equal to f1, which means it's equal to f -1 plus 2, right? Then it's the same, right? If you shift this by 2, yeah, you get the same value. Similarly, because the pattern continues, will repeat it, which means if I'm starting somewhere over here, I don't know what the value is. This is 0.7, for example. You have certain value, say this is 0.3. This is -0.7. This is 0.3. If you shift it to, this is f -0.7, which is -3. If you shift it to this point, make it also 0.3, you get f is 0.7 plus 2, which means this is pretty much 1.3, okay, which is f 1.3, which is also 0.3. So if you keep doing all the points, they're the same, keep doing the same, you're doing all the stuff, they're all repeated. Of course, you can also go from this point to this point. They also divide by, I should change this one too. Okay, let me change this one too. 3 and a 5. This will be the -3 and a -5. Okay. So if you keep doing this value plus 2, you also do the same value, right? You do the same value, which means, yeah, for every point, if you shift by 2 to the right, it's always to be the same value, right? Which means this is a periodic function. Okay, so that's a definition of a periodic function. Okay, and now given a periodic function, now we can define a period. So if ft is equal to ft plus this big T, now this for some positive t, this t is also called a period, okay, which is defined as a time range when a function ft repeats itself, which means you after this period, you get at one point. If you jump, you get some value, right? If you jump to this is t, you gotta jump to t plus t, you're gonna get the same value. Okay, it will repeat. Then this is called period. Okay, so for example, if for this case the period will be 2, right? This period for this example, the period is just 2. Of course, there's another property we can say, because if ft, let's say for example, if ft plus 1 equal to ft for all t, we can also say ft plus 2 is also equal to ft, okay, for all t. The reason is, if I do ft plus 1, t plus 2, which is equal to ft plus 1 plus 1, okay, I'm going to do this one. So because this is a property I have, so you sort of consider this like as a t, okay, t plus 1. Of course, t is equal to the black t plus 1. So this will be just ft plus 1 according to the property over here. Now, this is t plus 1. Again, you consider this as a t, so then you have ft. Okay, the reason that's being true, because if I look at this example, so this period is 2, right? It's 2. If I'm going to do 4, I'm going to double that. If I shift this one, not just f -1 is equal to f also -1 plus 4, which is f3, because you can keep doing it, because this guy equals this, right? This guy also equals this according to period 2. Of course, this guy will be equal to this, and this guy will be equal to this, so on and so forth. So for a period t, okay, So this is the integer number, any positive integer number time t is also a period of ft. Okay, that's what this property says. Okay, so observation is, if t is a period of ft, n t is also a period of t, so n is any positive integer. Okay. And also we have a definition called a fundamental period. Fundamental period says is the smallest period of t is called fundamental period. For example, if I give you ft, which is cosine t, for example, ft cosine t, now if I'm doing this is the drawing of ft, so when it's equal to 0, when t 0 is 1, when t is pi over 2 is 0, when t is 3 pi over 2 is also 0. Draw this picture. So the period is 2 pi, 4 pi, so on so forth, because cosine t plus 2 pi, which is also cosine t. Of course, I can say cosine t plus 4 pi is also cosine t. That's very natural, very reasonable, you know that. So the period can be 2 pi, 4 pi, and so forth, so 6 pi, and so on. So any 2 pi times n, basically, that's the period. And fundamental period is 2 pi, the smallest period, right? So it cannot be, because cosine, let's say cosine t plus pi, that's not is not equal to cosine t, because it's equal to negative cosine. So this is not true. So it's not a period. So you cannot have a period which is less than 2 pi. Okay. So if you do the cosine 2t, just do the inside, do the double of the t. So it's cosine 2t. If you draw it out, so this is what ft looks like for this new one. So when you t0, you gotta have a 1. When t is pi over 4 is 0, and 3 pi over 4 is 0, so on and so forth. So the period becomes pi, 2 pi, so on and so forth. We have n times pi, which is the period. Okay, the reason this is true, because according to the definition here, right, I have to have ft equal to ft plus t, right? That's the definition. Okay, let's say if I do that, it's a cosine 2t, right? So if I'm going to change t to t plus t, so it's change t plus, so I change this t to t plus, the period here is pi plus pi, right? Which gives us cosine 2t plus 2 pi, which is cosine 2t. Yes, that's true. That's why, yeah, it will be the same. That's why it's always true. So the period will be pi. Don't consider this as 2 pi, because you have to change it t plus t, okay? Because you have 2t, so you have to cosine 2t. You change t to t plus t, okay? Which is not equal to cosine 2t plus t, okay? That's different. Don't replace it in a different way, okay? Now the fundamental period for this case, it will be just pi, because you cannot find anyone smaller than pi, such that the cosine 2t plus t is equal to cosine 2t. You cannot find one if t is less than pi. That's not, you cannot find that. This is never true. Never true. So, and another property says, okay, so if I shifted, what if I shifted this one? The last example is ft equal to cosine t plus pi. I'm shift this one, which means you shift the function, right? This is called a shift ft to the left by pi. Okay, the shift doesn't change the period. The period is the same as cosine t. Okay, the period is the same as cosine. That's why we can say the period is still 2 pi, 4 pi. It's the same as this. Okay, so it will be 2 pi, 4 pi, and 6 pi, which would be just 2 pi times n. And the fundamental period is still 2 pi. So we can say that if our observation is that if ft has a fundamental period of t, now ft plus a can be any real number, also has a fundamental period of t. So this one is just a shift of ft, because the shift doesn't change the fundamental period. Some other properties for the periodic functions. if ft and gt are periodic functions with period t, they have the same period t. Now ft plus gt is also a periodic function with period t. Okay, this is very natural to understand because ft plus t plus gt plus t, you change it, right, which is equal to ft plus gt according, because they are periodic function, right? So that's why, yeah, if you put them together as a function, you sort of still have the same property, which means it still has a periodic function with period t. Okay, of course the period can have 2t, so on and so forth. Okay, the last property for the periodic function is called frequency. The frequency is defined, we typically use f, so don't get confused with the function itself and the period. So typically we use this f without a function. This is not different from function, which is called frequency. Frequency is defined by 1 over the fundamental period. Let's say the fundamental is f frequency defined by 1 over the fundamental period t. So the physical meaning of the frequency of the periodic function is that how many cycles given a period of time. Okay, for example, if I go back to this example over here, it's like I give it the unit period of time. I give it unit period of time. I give it unit of time. How many of these cycles? How many of this complete cycle? If I can, as a cycle is defined as a period. For example, you start from here, you end out here. This is called a period, right? A cycle. Like within 1 unit of time, how many cycles do I have? Of course, based on definition, it's just 1 over t, because it takes t time, which is a period, fundamental period, to get a cycle. That's why the number of cycles for a unit period is just 1 over t. Okay. And one property we can say here is the frequency, which is f, the fundamental period, which is t, the product of f times t is 1, because the number of cycles is just the inverse proportional to the fundamental period. Okay. For example, if I give you ft is cosine t, the frequency is 1 over 2 pi, because the fundamental period for this one is 2 pi. For ft is cosine 2t, the frequency is 1 over pi, because the fundamental period is pi. Okay, you can see this frequency is higher because apparently you can see 2t compares the 2t and the t, the 2t and t. So for the same period of time, so ft for cosine 2t, we have more cycles, right, compared to the ft. This is also related to frequency. Okay, so this is a basic introduction about the Fourier analysis. So next time I'm talking about how do I compute the Fourier series for a periodic function.